So it's my great pleasure to have Volker Branding here from Vienna, and he will talk about higher order generalizations of harmonic maps. Take it away.
So thanks you very much. I hope everything works out with the internet connection. Everybody can hear me, and I hope my internet connection will be stable today, because it's sometimes, this is the time of the day when everybody watches Netflix in Vienna and things might break down, but I hope it won't. So I want to talk about higher order generalizations of harmonic maps. And as the title already suggests, there's not one single generalization, but there are several. So let me give you a short outline of what I'm going to talk about. So I want to give a short introduction, basically to fixed notation, and give you some classical results on harmonic maps. Then the first higher order version I want to talk about are biharmonic maps, and I also want to show you two recent results on them, namely one unique continuation theorem and also one Liouville-type result. Then the next possible higher order version of harmonic maps are triharmonic maps, where I also want to show you some recent result. And then there's a systematic way to derive a family of higher order energy functionals, which are called r-harmonic or ES-r-harmonic maps. And this is the main part of the talk, and that's where I want to talk about later. And in the end, of course, there will be a short outlook. So what are harmonic maps, and what's the notation that I'm using? So for harmonic maps, we will always need two Riemannian manifolds, and my domain will always be called M, and will have a Riemannian metric G. And whenever I will choose indices, then indices on the domain metric will be labeled by Latin indices. And whenever I choose indices on the target, which will be noted by N and have a Riemannian metric H, then it will have Greek indices. So these manifolds will always be without boundaries, such that I can do integration by parts. Then I'm taking a map between these two manifolds. And for this map, I can associate an energy by taking the differential. If I square it, then have a function on the domain. And if I integrate it, I get out a number. So I get out an energy or action function. And if you write it down in local coordinates, then you get the following. So you see you have the first derivative squared. And in order to make a norm out of it, or to contract the indices, you need both Riemannian metrics. So you can already guess from here that the geometry of both domain and target will have a huge influence on this geometric variational problem. So what's nice about these energy functional, so it's invariant under conformal transformations if you're on a two-dimensional domain. And this is somehow special because all the higher order versions I'm going to show you throughout the talk, they will no longer be conformally invariant in any dimension. And these invariance under conformal transformation, it gives you a nice feature of harmonic maps if you're in dimension 2. So this is really something special and to keep in mind. Okay, but what are these mysterious harmonic maps now? So in order to get the harmonic map equation, you have to vary this action functional. And the first variation leads to the harmonic map equation, which is given by the vanishing of this guy here, which is called the tension field. And how is this defined? So you're taking the differential of the map, then differentiate once again, and take the trace over the two free slots. And this is supposed to vanish. And why is this called tension field? So this was in former times, or first used as a model for elasticity. Namely, you are thinking of your manifold M as some kind of elastic material, which you put on another geometric object, your manifold N. And if the material doesn't try to rearrange itself anymore, then its tension vanishes. So that's why people call this tension field. And formally, so this is a section in the pullback of the pullback bundle from the target manifold. So if you want to know what kind of PDE this is, it's good to choose local coordinates in order to get a feeling for it. And if you do this, and you see as a leading term, you have the Laplacian, so a linear second order operator. And you have a mild nonlinearity, so which comes here as first derivative squared. And again, you see that you need geometric data in order to contract the indices. And in case you haven't heard much about harmonic maps, you realize that this is a version of the geodesic equation. Namely, if your domain would be one-dimensional, then this gives you the equation for geodesics. Okay, now as we see, this is a nonlinear equation. So you might be worried that this equation doesn't have many solutions, or there may be few solutions or whatever. And one nice approach that I think one should always mention in the context of harmonic maps in order to prove their existence is the L2 gradient flow. So the idea here is you take an arbitrary map between your manifold M and N and deform it by a heat-type equation. And then you know heat-type equations, if you wait long enough, they tend to some equilibrium state. So you can hope when you do this deformation that if you wait long enough, your gradient flow, it converges your given map to a harmonic map. And why is this called L2 gradient flow? Because it also decreases the energy, so it tries to flow the harmonic map energy to a critical point. And this method can be applied very successfully in the case that the target manifold has non-positive curvature, and this gives this very famous theorem of Eells and Sampson, which is quite old, but I think it's like the first theorem in geometric analysis that uses such a heat flow method. So, and what does it say? So if both manifolds are closed and that the target has negative, non-positive is enough, non-positive sectional curvature, then this gradient flow has a unique smooth solution for arbitrary initial data. And if you send your deformation to infinity, then you get out a harmonic map. So this gives you a nice existence result. Of course, then the next question would be, what happens if you no longer impose this condition of negative curvature? Does everything work out as nicely as before? And the answer is somehow no. And this can be deduced, for example, from this following counter non-existence theorem. So Eells and Wood have shown, I think like 15 years later, so it was end of 70s, that there does not exist a harmonic map from the 2 torus to the 2 sphere. So this clearly has positive curvature with degree plus or minus 1. And this is a topological result. So it doesn't matter which metric on M or N you have chosen. And so this degree is something which is homotopy invariant. So if you try to deform such a map with the heat flow, then you know in this homotopy class it can never reach a harmonic map, so some singularity has to occur. And of course, there are results in this direction, but I don't want to go further here. Another nice feature of harmonic maps is that they satisfy a unique continuation property. So, and this is a theorem that was proven by Sampson, also rather old, 1981. And let me shortly explain this to you. So here we again also need to assume that M is a connected Riemannian manifold. And we are supposing that we have two harmonic maps, phi1 and phi2. And then the theorem tells us if these two agree on an open subset, then they are identical. And this in particular also implies that if you have a harmonic map which is constant on an open subset, then it has to be a constant map everywhere. So why is this a nice theorem? This is nice in the sense that the theorem you need to put in a local assumption and you get out a global statement. So usually it's the other way around. For example, if you have a given harmonic map, you like to deduce energy estimates on balls or whatever, and there it's the other way around. You're starting with something global and then use some cutoff function and localize your equation and deduce some local statement, but here it's the other way around. And the proof uses the famous theorem of Aronszajn, which I will also show you in a second when we present a similar result for biharmonic maps. And of course, you know such a statement from function theory for holomorphic functions. And there the situation is of course easier because you have a linear equation, and in the harmonic map case, this result still holds, but the harmonic map equation is nonlinear, so it's a little bit more difficult. But before I explain this result for biharmonic maps, let me also give you a short introduction to what are harmonic maps. So here, starting with something different. So again, it's a variational problem, but your starting point is the so-called bi-energy, and this is defined by taking the tangent field, and you are taking the L2 normal fit, and then you again get out a number, which you can then vary with respect to the map. And so the critical points of these functional E2, they are called intrinsic biharmonic maps. And the Euler-Lagrange equation is a fourth order PDE. Namely, as you see here, you have the tangent field. So this was the second order differential operator. and on it you have the Laplacian on the this vector bundle acting. So this gives you another two derivatives. So this is a fourth order term, which of course has lower order nonlinearities, but the leading term is the Laplacian applied twice. And here there's a second term in the biharmonic equation, which is also of lower order, but also the number of derivatives adds up to 4. So the tau is the second order differential operator, and here you have two first order derivatives. Right. So then here I wrote these are called intrinsic biharmonic maps. So this suggests.
So there is a question, sorry. There's
Yes?
a question in the chat, which is the geometric analog of this the Willmore functional?
If you take an immersion and you vary in the normal direction. So this is, did you hear me?
There's a thanks in the chat.
Okay. So I think it's okay. Okay, then I continue. But please, if there's something still unclear, then ask again. So these are called intrinsic biharmonic maps because they are defined intrinsically between these two manifolds. But the problem with this function is that it's not coercive. So it's very hard to get a nice existence theory. And you can get around this lack of coerciveness if you embed the target manifold into some RQ via Nash embedding, and then write down again a biharmonic map function or bioenergy for this extrinsically defined function. So this has the advantage that it's a coercive functional, but from a geometric point of view, you're unhappy about this. It depends on the embedding in the ambient space. So it's a little bit, if you're more interested in analytic aspects, you favor extrinsic biharmonic maps, and if you're more a differential geometer, then you probably are more into intrinsic biharmonic maps. But this is just a side comment. So besides it's fun to play around with these variational problems, why should you study biharmonic maps? So one thing that people always write in the introduction of the papers is, we know that there are situations where you cannot have harmonic maps. So maybe in these situations, there's a chance to find biharmonic maps. Then if you are looking for a scale invariant variational problem on a 4-dimensional domain, it's nice to have biharmonic maps. And of course, I already said the tension field has some application in elasticity. So you can also try to minimize the L2 norm of the tension field if you want to come up with a model for some elastic material. So also there you find biharmonic maps. And of course, you can always find these geometric functionals somewhere in string theory. Then something that you can immediately read off from both the functional and also the Euler-Lagrange equation is that every harmonic map is a solution to the biharmonic map equation, because it's an absolute minimizer of the functional. And also here you see in the biharmonic map equation, so if tau of phi vanishes, you always have a solution. So that's why you're in particular interested in biharmonic maps, which are not harmonic, and they have a name, so they are called proper biharmonic. And I will show some proper biharmonic maps later. Okay, now let's come to the first result on biharmonic maps that we recently assumed. And this is a somewhat generalization of this result from Sampson. So again, we have to assume that our domain manifold M is connected. And both of these theorems, they are joint work with Cezar Oniciuc, who is in Iași in Romania. And so here we are assuming we have a smooth biharmonic map. So if this map is harmonic on an open subset, then it has to be harmonic everywhere. And also we have this second version of the unique continuation theorem. So if we have two smooth biharmonic maps that agree on an open subset, then they have to be identical.
One question, sorry. How good has the target manifold has it to be analytic, or just any smooth or smooth enough thing works?
So it's just a Riemannian manifold, so it's smooth. It does not have to be analytic.
Okay, thanks.
Okay, so how do you prove this result? And I also already mentioned this famous theorem of Aronszajn, which Sampson used to prove his unique continuation result. So let me give this here. This is also quite old. And if you look this up on MassSciNet, it has a huge number of citations. So it's a strong result. And how does it work? So you're taking a A to be a linear elliptic second order differential operator, which is defined on some open subset of Euclidean space. And then you consider functions that satisfy the following inequality. So if you act with this elliptic operator on the function, then this is bounded by its gradient and the function itself. So if this inequality holds, then the theorem tells you if u is equal to 0 in an open subset, then it's 0 everywhere. So how can we apply this to biharmonic maps? So I think it's not, you would believe me that you could apply this result to harmonic maps, which are a second order equation, but biharmonic maps constitute a fourth order system. So how can you apply this second order result to this fourth order problem? And oops, to do so, we have to first of all write down the biharmonic map equation in local coordinates, where you can see this is some you don't want to do if you have to, but let me just shortly explain this. So as a leading term, you have, as I said, the Laplacian applied twice. So this is a linear fourth order operator. And then you have lots of lower order terms here. And apart from this term, all of them at the number of derivatives adds up to 4. So you have 3 plus 1, you have 2 plus 2, and so on. And this term, you pick it up from commuting covariant derivatives once, because you might have a domain which is non-flat, so we can not exclude curvature contribution and have to take this into account. And then you also see that all these coefficients here that we use to contract the indices, they are all given by geometric data. So these are the Christoffel symbols from the target manifold, and you could also write them as curvature if you like, but it's clear that in flat space they wouldn't be there, and all of them are geometric contributions from the target manifold. So if you're not interested in this whole duo of Christoffel symbols, and schematically this is an equation of this form where I wrote this with a star notation, which is just a short way of writing down all the contractions and putting all the Christoffel symbols in a function a of phi, then you see this is an equation of this form. Okay, how now to apply the Aronszajn result to this fourth order equation? And this works by defining new variables. So as we said, v is the differential of phi and w is the Laplacian of phi. And then it turns out that you can write any biharmonic map as a second order equation. Namely, you're defining a vector y, which is given by the map, its first derivative, and the Laplacian of the map, and it satisfies the second order equation. So this is somehow inspired when you have a linear ODE of nth order, then you can use the first order ODE by also having n variables, and that's somehow the thing that we do here. And so in this F3 now encodes somehow the right-hand side of the biharmonic map equation, and this is now manageable, and we can apply the Aronszajn result to it. So here I wrote on again this F3, which is now the right-hand side of the biharmonic map equation in our new variables. And now the strategy is as follows. So suppose we have two biharmonic maps, then we define this new variables v and w for both of them, and we are considering the difference between them. So this is now a function from Rm to this Euclidean space. So this comes by counting the dimension. It's in the vector here. And then you can apply Aronszajn's result to this difference of your two biharmonic maps. And in order to do so, you need some kind of estimate, which I wrote down, but this is straightforward to deduce. And we also use the mean value theorem to use this to count these theorems that involve the Christoffel symbols. And then in the end, you have reached this fourth order system to a second order system to which you can apply the result from Aronszajn. And if you think back here of how we defined this vector y, if all of these components have to vanish, it particular means that the first component has to vanish. So this gives us that the two maps in the end have to be identical. So this was somehow a shortcut to how to prove this unique continuation result. And we also got a geometric, so to say, corollary out of it. So if we are assuming that we have a biharmonic map, and P is a regular closed totally geodesic submanifold of our target, then this geometric unique continuation result says if an open subset of M is mapped into this totally geodesic submanifold, then all of M is mapped into it. And this result is somehow inspired by a result of Sampson for harmonic maps. And once you have this unique continuation theorem that I showed you before, you can straightforwardly generalize it. Okay, in the beginning, when I started talking on biharmonic maps, I said that every harmonic map is obviously biharmonic. And so can you find conditions when biharmonic maps need to be harmonic? And the quick answer is that the target has non-positive curvature. But before coming to that, let's also recall a classical result already from the 70s. So if you have a solution of the bi-Laplacian equation and the function is bounded from above and below, then, oh sorry, this should be an F, then it needs to be constant. So this is like a generalization of the classical Liouville theorem for harmonic functions. Then in the first paper on biharmonic maps, which was published by Jiang in 1986, he already proved that if you have a biharmonic map from a compact Riemannian manifold and the target has negative curvature, then it has to be harmonic. And this is really a straightforward two-line calculation by the maximum principle. So, but this tells you you don't need to look for proper biharmonic maps if your target has negative curvature. So in this case, you will always be back in the harmonic map business. In the case that you have a complete and non-compact Riemann manifold with positive Ricci curvature and a target manifold with negative sectional curvature, then collaborators proved that every biharmonic map with finite bi-energy must be harmonic. So this is like more a result when your domain is non-compact. And you can further find many further contributions, but they all somehow assume that the target has negative curvature. Now I want to show you some result where you don't have to assume negative curvature on the target, but still get that every map behind this result makes use of type equality. So this is an equality of the following form. You have here a certain power, certain LM norm of your function u, and this is bounded by the L2 norm of the gradient of u. And of course, C2 is a positive constant, and this, of course, depends on the geometry of your domain manifold. And we all know this equality in Euclidean space, namely it's the Gagliardo-Nirenberg inequality. But if you're on a Riemannian manifold, so of course you want it to be complete and non-compact in this case, then you have to be careful. Namely, not every non-compact complete manifold admits such an inequality. So you can construct weird geometric counterexamples where this is not true. But manifolds that admit such an inequality, then you say you have a manifold that admits an Euclidean type Sobolev inequality. So let's assume that we have such an inequality, then we can prove the following result, which is joint work with Yong Lu from Wuhan in China. So here we are supposing that M is a complete, connected, non-compact Riemannian manifold with dimension M bigger than 3 that admits such an Sobolev inequality, and the target is allowed to be an arbitrary Riemann manifold of bounded geometry. So then we are imposing two rather strong conditions, namely it has to be integrable in LP. P is allowed to be bigger than 1, and the LM norm of the differential of phi has to be sufficiently small, then the map must be harmonic. And if you furthermore require that M has positive Ricci curvature, then it even has to be constant. So these conditions are of course very strong, in particular this one, but let me emphasize that this is a somewhat natural condition because the LM norm, it's a scale invariant. So if you rescale your metric and this is small, then it isn't affected, so it stays small. So you cannot scale it away. It's not, although it's a strong condition, it's not a weird condition. How to prove this? And
so there is another question, sorry, on the chat, which is, isn't there an issue with the maximum principle for the bi-Laplace?
Right, but when you want, okay, so when you want to prove, for example, that biharmonic map is harmonic, you are somehow applying the Laplacian to the tension field. So in principle, you are applying a second order operator to something where you want to prove something about. So there's no issue. So if you want to, I guess this refers to this fact here, biharmonic compact manifolds and the target having negative curvature must be harmonic. So you prove it by applying the Laplacian to the tension field squared. And then you find out that this is positive, and then you know that it has to vanish. So there
yes,
it's
seems
usual...
to answer the question.
Okay. Okay, how do you prove this result? And okay, I said once you know how to prove it, then you're happy, because it's just taking a suitable test function, multiplied to the biharmonic map equation and do some estimates, but of course you have to find this test function, and this takes some time. So how do you set this up? You're taking a cutoff function in the usual way, so which is 1 on a ball, 0 on a bigger ball, and decays with 1 over r, the gradient. And then you test the biharmonic map equation with this test function. And here we introduced one delta, and this is for the following reason. P is allowed to be bigger, it's only supposed to be bigger than 1. So it could very well be that this this here is negative, such that we could probably divide by 0 if there would be zeros of the tension field. And just to avoid this, we are adding here some delta. So this is some trick inspired from Yau, which he used in similar calculations for harmonic maps. Then you test the biharmonic map equation with this guy, and you get the following inequality. So here's something on the left-hand side, which we want to show that it's 0. And what do we have on the right-hand side? So here we have a term where we first want to set delta to 0. Then you see here we have what's remaining is a tension field in the LP norm, but this is supposed to be finite. So if we are sending r to infinity, this term will go away. And somehow now we have to find a trick to absorb this term on the right-hand side into the left-hand side. And there we use this Euclidean type Sobolev inequality, namely you can play around with this term and find that it is bounded by the LM norm of the differential and the same term that's on the left-hand side. So this term will again go to 0 when you send r to infinity. So what you do then, you're choosing this small enough, then you can absorb everything from the right-hand side into the left-hand side, and then you can do some further calculations and find that you have a harmonic map. So that's how this proof goes. Once you know how to do it, it's very straightforward, but of course, like always in these things, you have to find the trick. Okay, now you could get the impression. I showed you several guys that maps need to be harmonic, so you could think this is always the case. And of course, there are some proper biharmonic maps in the world, but what you have to do, you have to consider a target which has positive curvature. So the first thing that you can find by an explicit calculation is a map that we are all familiar with. So it's the inverse stereographic projection from Euclidean 4 space to the 4 sphere. This turns out to be proper biharmonic. So it's not harmonic. And the first bigger family of proper biharmonic hypersurface was found by these 4 persons, and this was in several papers around 2001. So if you consider proper biharmonic hypersurface of the Euclidean sphere of dimension m+1, then they are, for example, hyperspheres or products of spheres of radius 1 over square root of 2. So where these both dimensions up to m and they're not allowed to be equal. And what's really important to take away, because I want to show a generalization of this result later, is that biharmonic here requires that your sphere has radius 1 over square root of 2. So these 2 and these bi, they somehow correspond. And the conjecture at the moment is that these are the only proper biharmonic hypersurfaces, but this seems really hard to prove in this more comment. Okay, before we come to the polyharmonic map case, let me show you one generalization of higher order, which is a tri-energy. So the tri-energy is, you're starting again in the tension field, but now you're taking a covariant derivative of it and take the L2 norm of this guy. So this is a 3rd order derivative here in the energy functional. And when you vary this, you got the triharmonic map equation. And this is now of 6th order. As you see here, you have tau again, the tension field, which is a 2nd order operator, and you apply the Laplacian twice, so you get a 6th order term here. And on the right-hand side, you have again 2 curvature contributions, and the number of derivative adds up to 6. So here are 4, 5, 6, and here is 3, 5, 6. So this scales in the right way. And so we will see an explicit example of such a solution to the triharmonic map equation later. And there's really not much known about them. And for example, one result that was known was—
There is a question.
Yes?
Sorry. So there's a question. Biharmonic hypersurface means that the inclusion map is biharmonic? Question.
No, it means that it's isometric immersion, the map. So it satisfies the biharmonic map equation, and at the same time, it's an isometric immersion into a submanifold.
Okay, I actually have like another question. I don't know if there's a follow-up in the chat, but the domain, you don't care about the dimension of the domain?
In which result, or where?
In the previous results, that harmonic is biharmonic, no, the other way around. Biharmonic. Yeah. Say again?
Are you in the list?
Ah, yes. So in this you have dimension m is larger than 3, I just saw.
Yeah, right, because you only have this Euclidean Sobolev inequality on dimensions bigger than 3 equal. So here it's...
but you assume that you're already smooth. So all these possibly singular solutions of the equation are ruled out a priori.
Yeah, right. So we are always here in the smooth case.
Okay, okay. Thanks.
Okay, so what was known about these triharmonic maps before? It was known that if you have an immersion into a Riemannian manifold, and this has non-positive curvature and energy is finite, then they need to be harmonic. And I was able to generalize this slightly or give a different, similar result. So here we are assuming we have a smooth triharmonic map from Euclidean space, and that we are not in the critical dimension. So the critical dimension would be 6, but we have to rule out this. And again, we are supposing that a certain energy is finite. Then if m is equal to 2, every triharmonic map must be harmonic, and if m is bigger than 2, then it must be constant. And just as a comment, I don't think that it's easy to generalize this result to a Riemannian manifold instead of if you want to replace Euclidean space by a Riemannian manifold. Okay, let me shortly give an idea how to prove this. So if you analyze the tri-energy, then you find it has a nice invariance. So if you consider a diffeomorphism on the domain U, then you find if you pull back the domain metric by this diffeomorphism and compose a map with it, then the energy remains invariant. So this gives you by Noether's theorem a conserved quantity, which is a stress energy tensor. So you have to vary this functional with respect to the domain metric. And then this gives out this quantity. And because it's conserved, its divergence vanishes. So you can take the divergence of it and test it with something nice. And again, you're choosing a special kind of cutoff function. So again, which is 1 on a certain ball, 0 outside this ball, and decays sufficiently fast. And then you calculate the following. So here you have 0, which comes from taking the divergence of the stress energy tensor, and you test it with this combination where eta is this cutoff function that I described before. And then you have to do integration by parts and estimate all these terms coming from the stress energy tensor. And this gives you the result in the end when you take the limit r to infinity. And this is also the reason thing that you can generalize this to a Riemannian, because this is a globally defined conform vector field space, but you would need something else, something of the same kind on a manifold if you want to generalize this. And these vector fields, of course, only exist if you have enough symmetry. Okay, so far it was a short excursion triharmonic maps. And now let's come to higher order energy functionals. So this story already began in the first paper by Eells and Sampson in 1964 on harmonic maps, where they proved their nice result that I showed you in the beginning. And this was later again suggested by Eells and Lemaire in '83. So they have a famous book, which they call Selected Topics in Harmonic Maps. And there they write down a lot of interesting problems. Many of them are answered by now. Many of them are still open. And one thing that they suggest to study is the following. So a polyharmonic map of R-k is an extremely of the following energy function. So you're taking the differential plus the co-differential, apply it k times to a map and take the L2 norm of it. And then they also say if k is bigger than m/2, so above the Sobolev threshold, then this function satisfies condition C of Pell-Ismail. Therefore, there's a polyharmonic map of order k in every homotopy class. So it would be very nice if this is true, but unfortunately, they don't give a proof or a hint how to prove this or where to find this. And I'm not sure if it's true, but I will give some comment on this later. So what I'm going now to tell you is joint work with Stefano Montaldo, Cezar, Oniciuc, and Andrea Ratto. And we are very happy that our paper just got accepted in advances. So first of all, let me explain a little bit how to make sense of this function. So we had to give it a name. And because it was suggested by Eells and Sampson, we called it the Eells-Sampson R energy. I wrote it down here again. And first of all, recall, so the co-differential is an operator that decreases the degree of map or of a function. And the map you can think of as a something which has degree 0. So when you apply the co-differential, you have to get 0 because you cannot further decrease the degree. And also, you know, from exterior algebra, if you apply the exterior derivative twice to your map or function, then you get 0. In this formalism with differential forms, you can write the tangent field in the following way. So you take the differential and then the co-differential. In this convention, one should use minus sign here. So let's see, what do we get for low values of R here? If we insert 1, then we're getting d phi squared. So this is the harmonic map energy we already studied. If we take R equal to 2, you're getting the tangent field here. So this leads to the bi energy. If you take R equal to 3, then you're getting the tri energy that I showed you before. So far, this seems like a convenient way to write down the energy functions that we studied. So, and maps were already studied by several people in the literature. I always said, let's study this functional. So if we want to have an even number here, then let's apply the Laplacian suitably often to the tangent field and take this as a starting point. Or in the case where you have an energy of an odd number, let's take the gradient here and apply it in this form to the tangent field suitably often. So as you can check by explicit calculation, the critical points of both of these functions, they lead to semilinear elliptic PDEs. As the part, you always get the Laplacian applied k minus 1 tangent field plus many lower order terms containing curvature on the right hand side. So this can be calculated explicitly. And most of these articles claim that these two functions for polyharmonic maps were the ones that are suggested by Eells and Sampson. And this somehow is true in the case R equal 1, 2, or 3. And this is I think this comes from the more only work with these low values of R, so you don't see the difference. But when you take R4, then there comes a difference, and that's the starting point of our project somehow. So that means why there is a difference between this Eells-Sampson and the polyharmonic map function. So if you put R equal to 4 in Sampson energy, and you write it in the following way, so you have d plus d star square acting on the tangent field. Now you can think of the tangent field again as a 0 form, but it's a 0 form which takes values in a vector bundle, namely the pullback bundle from the target. So this is now different than a map, which doesn't take values in some vector bundle. So if you compute this square here, you're getting 2. So first you have d squared twice, then you're getting a 2 form. And there's another contribution you get by which comes from applying D and then D star. So this is a 0 form. This increases the degree by 1, but here it's already lowered by 1. So this is a 0 form. And now we have here a scalar product on the bundle of all forms, if you want to formally think of this. And forms of different degrees, they are perpendicular. So we're getting 2 terms here, namely this 2 form and here the 0 form. And if you analyze this 2 form, this is exactly is the curvature target that comes out here. So this term is equal to a curvature contribution. And here you have the Laplacian acting on tau, which you can write it like here. But this shows you that this Eells-Sampson energy and the polyharmonic map for energy that was studied before, they differ by this curvature term. And of course, it's very difficult to really find a difference between these two variational problems. This is a 4th order energy functional, so the critical points are of 8th order. And if you want to find, here you're adding a lower order term, and to find a difference really is really hard. And this that would be nice to achieve, but yeah, so far we couldn't. Okay, but still, let me give you some results on these Eells-Sampson higher energy functionals. So first, some terminology. So we call solutions of this ES-r-harmonic maps. So because r-harmonic map was already taken for these polyharmonic maps. And then we say, as in the case of biharmonic maps, that such a map is proper if it's not harmonic, because harmonic maps are always solution of these higher order variational problems. And again, in the case when we have an isometric immersion, then we say it's proper if it's not. So a harmonic map, which is an immersion, is minimal. And we want to rule out this case here too. So in the article, we calculated explicitly the critical points in the case of r equal to 4, and this was really nasty. And of course, you can do it in the case r bigger or equal to 5, but this will be really not something which one likes to do. Okay, now let me show you some existence results. So is that the number r is greater or equal to 2, and the dimension of the domain also. Then the hypersphere from the sphere of radius big R into a sphere of dimension m plus 1 is a proper ES-r-harmonic submanifold. This should be Sm plus 1 here, sorry. If and only if the radius is equal to 1 over square root of R. And recall, I showed you this result for biharmonic maps where R was equal to 2. And we can generalize it to arbitrary high order. And you see here the order of the ES-r-harmonic map shows up nicely here in this radius. There's a second result of a similar spirit. So we are considering some generalized Clifford torus. Again, R is supposed to be greater or equal to 2. Then we're taking two numbers P and Q, bigger, supposed to be greater or equal to 1, and two radii, whose square adds up to 1. Then we are considering this generalized Clifford torus. So you have one sphere of dimension P with radius R1 and another one of dimension Q with radius R2 sitting in a sphere of 1 dimension higher. So this is minimal if these condition holds. So that's not so interesting for us. But the second statement of the theorem tells us that a proper ES-r-harmonic submanifold of this sphere if and only this does not hold. And in the case where R is greater or equal to 3, we can determine such a submanifold by the roots of the following polynomial. And you see this is a polynomial of 3rd order in the square of the radius. So you cannot expect to find solutions of it for arbitrary P and Q, but you can convince yourself that there are situations where there is a real solution, so that you get a proper ES-r-harmonic submanifold. Let me some idea how to prove this. So the most complicated thing, of course, you could do is try to calculate the critical points of these functionals and then to solve the Euler-Lagrange equation. So this would be extremely complicated because we allow R to be as large as you like to. So it seems very suitable to choose a different strategy and to exploit the symmetries. So by an explicit calculation, you can show that this is invariant under isometries of both target and domain manifold. And then there's a very nice principle of Palais, which is called symmetric criticality. And it tells you the following. If you have two Riemannian manifolds and a compact Lie group, which acts by isometries on both these Riemannian manifolds, then if you have a G equivariant map, so a map that is invariant under the action of this Lie group, then this map is a critical point of this Eells-Sampson energy if and only if it is stationary with respect to variations which are G equivariant. So this basically tells you you're allowed to first reduce your energy functional to symmetry reduce it, and then calculate the critical points, and you do not lose something. And because the both theorems that I showed you are in a spherical setup, so it's very natural to apply such a procedure, and we are using all the symmetries of the sphere to reduce this variation problem to a one-dimensional thing, basically, namely only what you have to do in the end is determine these radii R1 and R2. So this seems like a very good strategy for this higher order variation problems. Of course, there are many steps involved, which I didn't tell you now, but that's how we got those results. Then it turned out that both of these maps that I showed you in the last theorems, they are critical for both of these energy functionals. So these curvature terms that are coming from the Eells-Sampson function, they are zero if you evaluate these maps on them. We hope to find something new there, but coming from this curvature term, but here you cannot find it. Maybe there's if you calculate the second variation and analyze the stability, you could find something, but this computation also would be very demanding, and we didn't do it. And in the last 3 minutes, let me show you some other critical points we could construct for these ES-r functional. So when we consider maps from the punctured Euclidean disk, so we are taking a disk and take out the origin into a sphere, which are of the following kind. So omega is mapped.
So there is another question. Sorry. Yes. Would one expect global minimizers to be necessarily G equivariant?
Sorry, one?
Would one expect global minimizers to be necessarily G equivariant?
Oh, that's a good question. I guess in the spherical setup, maybe yes, but in general, I mean, it's so far not even clear that we have a minimizer, and so that's a good question. And to be honest, I'm not sure.
All right, thanks.
So the strategy that we are pursuing here is similar. So by making lots of symmetry assumptions, we again are left with some one-dimensional variation problem, namely to fix this number alpha prime, alpha star. And when you do all the computations, which I didn't show now because you don't want to see them if you have to, then it turns out that you can maps of these form here, they are critical points of, again, both the ES-r-harmonic and the four-harmonic energy, but only if the dimension is 8 or 9. And so where does this 8 or 9 come from? So you're getting an algebraic equation for alpha star, and it turns out that it only has real solutions in dimension 8 or 9, which is also nice because 8 is a critical dimension for both of these functionals, and it's of course the dimension where you're interested in finding solutions. Then there's another class of maps where you could prove the existence of critical points, namely these are conformal diffeomorphisms into a cylinder. And here we are taking maps from Euclidean space with the origin removed, and the target is a cylinder, so you have a sphere of dimension n-1 times r, and considering maps of this form. And I think for time reasons, I won't go into the details here, but you can find, depending on dimension and on the order of your Eells-Sampson functional, again, critical points, but it turns out that they are, again, both critical points of the Eells-Sampson and the r-harmonic energy. And the proof here uses induction on the dimension. So we guessed it somehow in low dimensions and then could use induction to go to the general theorem. So finally, let me make a remark on condition C. So I showed you this excerpt from the book of Eells and Lemaire, and they said that these ES-4 or ES-r functionals satisfy condition C, and which already would give you an existence theory. And we don't have like a real counterexample, but the following observation: when we have the flat 2 torus, then the following holds. So if you take the infimum of the Eells-Sampson 4 energy over all maps from the 2 torus to the 2 sphere, where the map has degree 1, then this is 0. But on the other hand, you can easily convince yourself that also the following holds. So the function does not emit a minimum in the homotopy class maps from the 2 torus to the 2 sphere of degree 1. Why is this the case? Because this would need to be a harmonic map, and I showed you the result of Eells and Wood in the beginning that tells you that there isn't such a map. So this at least tells you that you cannot expect to find a minimizer, but maybe there's only a critical point, and it's not really clear what Eells and Lemaire wanted to say when they wrote down remark on condition C in their suggestions. So this proof is again inspired by correspondence from Lemaire for biharmonic maps, and it seems that you could also extend it to a higher order, higher R. And of course, there is still much to be stood. What's the relation between condition C and these higher order energy functionals? So now let me come to the outlook. Of course, there are many things you can do with this higher order energies. Having a general existence theory would be nice, but of course it's very hard. Then we have seen that biharmonics often tend to be harmonic if the target has negative curvature. So this is also true in the higher order world. This is also would be interesting. Stability is of course always interesting, but calculating the second variation of these functionals is really not something it's straightforward to do in some sense, but it's really demanding. And better understanding of these curvature terms would also be something that's very nice to have. So there are many things one can do, and I would like to thank you for your attention, and I don't know which order is the best, but maybe the case one, and bye-bye.
All right, thank you very much. Other questions, remarks, comments?